Hello, everyone. My name is Alphose Zingoni. I am a professor at the University of Cape Town, South Africa. The title of my presentation is Symmetry-generated space grids. The aim of this work is to show how symmetry groups may be used as a tool for creating complex space grids. Due to time constraints, I will only present the basic ideas here. For details, reference should be made to the written paper. Why should we want to create symmetric grids? Symmetry is not only aesthetically pleasing, but also enhances the functionality of physical spaces. Symmetry reduces the cost of assembling the structure as it allows the use of repetitive units in a systematic sequence. Symmetry allows use of group theory to simplify computations, and symmetry allows the physical behavior of the structure to be more predictable. For example, its vibration or bifurcation characteristics. Let us start with a quick overview of symmetry groups. In algebra, a set of elements constitutes a group with respect to binary operations if certain axioms are satisfied. A symmetry group is a particular type of group where all elements are symmetry operations. Symmetry operations are typically reflections in planes of symmetry, rotations about an axis of symmetry, and rotation reflections, i.e. a rotation combined with a reflection in the plane perpendicular to the axis of rotation. In the present context, we're only interested in systems that have a center of symmetry. That is a point whose position remains unchanged under the application of any of the symmetry elements. The symmetry groups of such systems are usually referred to as point groups. Point groups may be classified based on the type of elements making them. Groups Cn and Cnv possess a single n-fold axis of rotational symmetry, with Cnv groups having additional n reflection elements. In spatial configurations, there are groups with one n-fold principal axis as well as a system of two-fold secondary axis at right angle to the principal axis. These are the dihedral groups Dn of order 2n. If we add a horizontal plane of symmetry to this, we obtain groups Dnh with 4n symmetry elements. Regular polyhedra are associated with more than one n-fold axis of symmetry where n is greater than 2. The tetrahedral, octahedral, and icosahedral groups, denoted by T, O, and I respectively, contain only pure rotations. Adding reflection planes to the groups T, O, and I gives group TD, TH, OH, and IH of higher order. Clearly, the number of possibilities for spatial configurations is quite large. Here are some examples of configurations with tetrahedral, octahedral, and icosahedral symmetries. So how do we use symmetry groups to generate space grids? Let eta be a basic structural unit of a space grid in a frame of reference defined by the rotation axis and reflection planes of a symmetry group G of order n, having elements alpha 1, alpha 2, up to alpha n, where the first element alpha is the identity element E. Applying the elements of G on the spatial configuration of eta, we obtain E alpha 2, alpha 3, up to alpha n times eta is eta 1, eta 2, eta 3, up to eta n. Let's call that H, where eta 1, eta 2, eta 3, up to eta n are the various spatial positions of eta as generated by the symmetry elements E alpha 2, alpha 3, up to alpha n. And H, which is eta 1, eta 2, up to eta n, is the collection of all spatial configurations, which taken together represent the generated space grids. The vertical bar notation here denotes that the units are connected to form a structure. The configuration of H belongs to the symmetry group G, and the physical properties of H, such as vibration or stability behavior, will be characteristic of physical systems belonging to symmetry group G. Equation 1 is the basis for generating larger space grids using symmetry groups. Let us consider a few examples. Double layer and triple layer rectangular space grids may be generated from simple basic units using symmetry groups of two-fold or four-fold symmetry. Figure 2 shows two basic space truss units in the form of a right square pyramid. This belongs to the symmetry group C4H. And a right octahedron. This belongs to the symmetry group D4H. If all 12 members of the octahedron truss have equal length, the configuration becomes a regular octahedron, which belongs to the higher order symmetry group OH, to which a cube also belongs. We may apply the elements of symmetry group C2V, namely EC2 sigma x and sigma y, to the basic unit eta is equal to A1 to obtain the full space grid H, shown in plan in the diagram on the left. If A1 is a square pyramid, we get a double layer grid, figure D. If A1 is the octahedron, we get a triple layer grid, which is figure E. Clearly, the triple layer grid of figure E could equally be generated by adopting the square pyramid as the basic unit eta is equal to A1 and applying the 8 symmetry elements of group D to H to generate all 8 pyramidal units of the grid. Large-scale space grids with many panels may be generated by selecting representative basic units and applying the elements of the appropriate symmetry group to each representative basic unit eta to form a permutation set. The full space grid is the sum of all the permutation sets. The grid shown in this figure is generated by permuting the representative basic units A1, B1, C1, and D1 through the 4 symmetry operations of group C2V. The permutation sets are Q1, Q2, Q3, and Q4 as indicated in the figure, which when combined give the assembled group double layer space grid H. The same grid could have been generated more efficiently using 3 representative basic units instead of 4, by permitting the representative basic units A1 and B1 through the 4 symmetry operations of group C2V, and the representative basic units C1 through the 8 symmetry operations of group C4V. The results of these permutations are as follows. The permutation sets are Q1, Q2, and Q3, where Q1 and Q2 are generated using the 4 elements of symmetry group C2V, while Q3 is generated using the 8 elements of symmetry group C4V as shown in the figure. Combining the 3 permutation sets, we obtain the full space grid H. In general, large-scale rectangular grids can be generated through the use of symmetry group C2V only, while large-scale square grids are more efficiently generated through the mixed use of symmetry groups C2V and C4V. It is also possible to create variants of rectangular grids reflecting all or some of the symmetries of CNV and DNH groups. Figure 3a shows a basic unit eta is equal to A comprising 3 pyramid trusses arranged into an L shape. Applying the 4 symmetry elements of the cyclic group C4V on the initial configuration A1, we obtain H as follows, where H is the generated double layer space grid. Note that H is the cyclic symmetry group C4. Successive application of symmetry groups can create bigger and more complex configuration space grids. This may be successive use of the same symmetry groups or successive use of different symmetry groups. The symmetry group of the final configuration may be of higher order than the groups that were involved in the successive operations. In this figure, we see successive application of 3 symmetry groups to generate a triple layer space grid with 64 panels and 760 members. Starting from a single pyramid, a complex space grid of higher order symmetry is created through the successive application of symmetry groups C1V, C4V, and D2H. Triangular and hexagonal grids may also be generated in a similar fashion. Starting with tetrahedral truss as the basic unit, we may use symmetry groups C3V with 3 rotations and 3 reflections, and C6V with 6 rotations and 6 reflections to create the following grids. In summary, it is clear that generating structural forms using symmetry groups is amenable to automation. The key steps of the automated process are: define the center of symmetry, select the desired symmetry group G, and define all axes of rotation and planes of reflection. Place the basic unit in the desired position and orientation with respect to the center of symmetry, rotation axis, and reflection planes. Execute a single command to generate the full structure by applying all symmetry elements of G on the basic unit. If desired, repeat for other choices of symmetry group and object and combine the results to obtain structural forms of higher complexity. In conclusion, in this contribution, we've seen how symmetry groups may be used as a tool for creating complex space grids. This is achieved by applying chosen symmetry groups as operators on the position and orientation of one or more basic units. The key steps in the automation of this process have been indicated. It remains to develop algorithms that allow the rapid exploration of novel spatial configurations of higher order symmetry. Thank you.